Alright, right now we're going to take a look at finding the area underneath polar curves. And so you've been doing polar derivatives, hopefully that's coming along nicely, but now we want to focus on area. And thankfully this is actually fairly simple, but you have to go back to something you've seen before, areas of sectors for circles. So I'm going to draw a few things. We got a polar curve over here on the right, and we want to eventually find the area inside one of these petals. And first thing, you have to change a little bit of what you think of in terms of area. Oftentimes we think of area underneath a curve like this, a whole bunch of rectangles. That's not quite what this is going to be. Instead, you need to think of this as area of a whole bunch of radii. So think of the radius that comes out to these points. That's a radius. Then another radius and another radius coming out. That's what you want to visualize your area as, because that's what our integral, which we'll be getting to, is going to find as this red point comes around our curve. We're going to be finding the area from that point to the center, not rectangles underneath the curve to the x-axis like we do in rectangular form. So what we essentially have here are a whole bunch of sectors. You've got, say, a point here and a point here, and you want the area of that sector right there. And so we have to remember, how do we find the area of a sector of a circle? It's very similar, and that's where the formula comes from. So how do you find the area of this sector? Well, you start with the area of a circle, which is just pi r squared. But if you only want part of the circle, you have to think, all right, what angle theta are we looking at? And so the area of a sector is equal to however big your angle is divided by the total amount of the circle. The total circle is 2 pi. Kind of gives you a percentage. What percentage of the circle are you looking at? Oops, not equals. Sorry about that. Times the area of a circle, pi r squared. That would give you the area of a sector. Now the pi's cancel out, so the area of our sector is simply 1/2 theta r squared. And hopefully you can realize that that's a big sector, and as we take a look at our sector over here, once we start taking the area of the entire things, that sector, this change in theta is going to be going to 0. We're going to make it as small as possible. We're going to have an infinite number of sectors, and then we're going to add them all up. And to kind of help you see this next step, I'm going to rewrite this as 1/2 r squared times delta theta. Just moving the theta to the back and realizing that theta is actually a change in theta. So we're going to add all these up. What calculus idea adds things, an infinite number of things up? That is the integral. So we're going to take the integral, and we're going to take the integral of this whole thing. 1/2 r squared delta theta, which is just d theta, which is of course will approach 0, which is why it becomes d theta. And of course our integral, if it's an area, it will be a number, so we have to go from some letter a to some number b. Although I suppose more accurately, those stand for angles, so it will be some theta 1 to some other angle theta 2, depending on how far around your curve you're going. And so there you have the formula, although we can use a few properties of integrals. You can take the 1/2 and put it on the outside. So this is what you'll usually see in your book. That is how you will find the area of polar curves. So I'll put a nice big box around that. And one more time, when you do that, you do need to be careful. You are not finding area this way with rectangles. That's not what we're doing here. We are finding sectors, and so your rectangles, I guess you could say, go to the center. So from there to there. That's the type of area we're looking at. It makes a pretty big difference, mostly for your limits. What numbers do you pick for theta? That's usually the hardest part. So to show you how that works, I'm going to do an example. So we are going to look at the equation r equals 2 cosine of 3 theta. And so I'd encourage you right now, can you draw that on your calculator? Just so happens to be the graph I have here on the right. And we want to figure out the area of one petal. Okay, we want the area of one petal. So you see we have 3 petals over here on the side, and we want the entire area of one petal here. It actually, in this case, doesn't matter which petal you look at, they are all the same. So you could do that one, you could do this one, or you could do this one. Either one works just fine. So we are going to start off with an integral. 1/2 times the integral of r squared. Well, r is simply the function 2 cosine of 3 theta. And make sure you square the whole thing, so that will eventually become a 4. But right now it's just a 2. Make sure it also gets squared. Alright. Make my integral a little better. This is d theta. And now the hard part. What are the limits? That is going to be the hard part. How do we draw, or how far is it from here to here, and then around this way, I suppose? We're not quite sure right now. And so your calculator can help you with that. If you graph this again and actually watch it draw the function, that can sometimes give you a hint as to what you have to do. So here I have a nice little animation of that. So let me start from the beginning. This is kind of cool. You see the polar curve here on the left, and on the right you actually see the sine function. Or sorry, in this case the cosine function. So that's pretty nice. Actually, I gotta make sure here that I've got the right function. There we go. 2 cosine of 3x, or 3 theta is what we're doing. A little bit bigger. So watch the red dot as we draw. So here we start at 0, and then theta increases, it comes up, goes past the origin, then goes down, around, up, and over, and we get back to 2. We get back to the beginning. If you take a look at the blue dot on the right over here, right at pi. So we've done an entire revolution when theta equals pi. So theta needs to equal pi will give us 1 full revolution. Okay? But if we want to do this first petal, you'll see that the dot, let me get back here, the dot starts out in the middle of the petal at theta equals 0. Then it moves up and along, gets to the center, and then it moves to the second petal, which is a problem because we only want to look at the first petal. So if we go from theta equals 0 to the origin, that only gives us half the petal. That gives us this area right here, which is only half of what we want. But it's still good to know where are we here when the red dot gets to the center. So we've got to do a little bit of math here. We've got 3 petals, and the entire period is pi. So each petal is going to be pi over 3, but of course we've only traced half the petal. So half of pi over 3, these are not equal, gives us pi over 6. So here we're at the point 0 comma pi over 6, which is only half the petal. Well, if 0 to pi over 6 gives us half, and we want to go backwards along this petal, that means this point over here is also 0 comma negative pi over 6 if we wanted to go backwards. And so we're going to start at negative pi over 6 and we're going to end at pi over 6, which of course that distance from negative pi over 6 to pi over 6 does give us a complete pi over 3, which is 1 petal. Okay, so now that we know the limits, we can go back and finish our integral. So let me erase the highlighting here. So we're going to go from negative pi over 6 to pi over 6. You can plug that integral into your calculator, and here's the 1/2 on the outside, times you will get 2 pi over 3, or a decimal equivalent, so double check that. And then when you multiply those out, you will get pi over 3 as 1 petal. Okay, so that is not the only way you could get the answer. We went from negative pi over 6 all the way around to pi over 6. You could have also done the second petal, the green one down here, which starts at pi over 6, because that's the origin here, and then goes around, and 1 petal is pi over 3, so that would be another pi over 3 plus pi over 6, which would be 3 pi over 6. Yeah, pi over 6, 2 pi over 6 would get you to here, 3 pi over 6 would get you back to the center. So you could do the integral from pi over 6 to 3 pi over 6, which is just pi over 2. I'll write it as 3 pi over 6, that probably makes more sense. 3 pi over 6. You could have also then started at 3 pi over 6 and gone over to 5 pi over 6. As long as the difference here is pi over 3, you're good, or 2 pi over 6. That will get you 1 complete petal. And so that can be a little hard, figuring out what are your limits. I think I'm reaching the limit of my video here, so I'm going to stop it and then do one more short video to tell you a little bit more on how to get those limits, especially without your calculator, which you might have to do.